a two-class classification. So the weights is initialized randomly. So at first there is no preference on the weights. Then while we reach the stock criteria, while we are sure, okay, the model is it's learned whatever it could learn, we will continue this training loop. And the training loop was to choose a random sample from both positive and negative classes, so either positive or negative. If the sample is positive, but the output of this neuron or output of this perceptron is negative. So sample is positive, we expect it to be generate positive, but it generates a negative value. If it's negative, it's not correct, then we increase the weights by amount of x because we want to increase this weight time x, this result. We want to increase it. So we add some value to this w, and that value would be amount of x itself. And we hope that if we add again to the w again and again and again, this result would be positive. If it's negative, sorry, if it's the sample that I'm choosing is positive and the result is also positive, I'm doing nothing because it's throughout my expectation. If the sample is that I'm choosing is negative, but the output is positive, this time I reduce some value from W to decrease the overall the summation, the overall output. So, and if the sample that I'm choosing is negative and the prediction is also negative, then I'm doing nothing. I do this approach again and again, and there is a mathematical proof that it converges at the end. If there is a solution, it's converge at the end, and it can find the solution. So it adjusts. Sometimes it increases this weight, sometimes it decreases this weight. Adjust this weight again and again until for all of these samples, the output is the same value that I expect. And when they were starting using it, people were very happy. They were excited. Okay, this is very good. This is working very well. Training is easy, straightforward. But there was one issue. And the issue was this training algorithm only works if we have one neuron and one layer. If we have more than two, we couldn't do this increase and decrease with the weight. It didn't make sense anymore. And with only one layer, we were not able to solve nonlinear problem. And the most famous problem here was the XOR problem, that there were no perceptron to be able to solve this problem, a very simple nonlinear problem. And when they saw the issue, they stopped using perceptron. And so something happened in those years. They called it the winter of AI. That people stopped using using and developing machine learning models, and they say, okay, the perceptron was the best thing that we could do. We cannot get anything better than that, and perceptron is not good enough. But later in around 1980, 1986, if I'm not mistaken, then they come up with another activation function, which was sigmoid, and they come up with another training approach, which was able to train more than one layer. And then they started the area of training larger neural network, and then to this day that we have very deep neural network. So this one is a very simple neuron. If we put bunch of these neurons together, then we have one layer, fully connected, feed-forward neural network. So it's a network of neurons, so it's neural network. It's feed-forward because the information goes only in one direction, from the input toward the output. And we have only one layer of weight, sorry, one layer of weights, so we call it one layer. We call it fully connected because each neuron in each layer is connected to all previous information. If it's input or if it's another layer, everything is connected to everything. So it's fully connected. So again, one layer, fully connected, feed-forward neural network. Here is two layers. So we have two sets of weights. It's feed-forward. Information goes from input to the output only. It's fully connected. All neurons in each layer is connected to all neurons in the previous layer or to the next layer. So it's fully connected. That's it. That's the general idea of neural network. We have, other than feed forward, we have a skip connections, we have recurrent connections, we have neurons that are not connected to all previous layers. We will see them in a bit. But the general idea is to combine these neurons in some structured way together. And if we can train such a network, then the neural network is like playing Legos. These blocks are each neurons or each layers, and the art of neural network is to put them together in a way to build something that works for you. Which how you have to put them together. You need to practice, you need to play with it, you need to see your validation set. But the general idea is to put everything together. And there are many different ways of connecting these neurons together. So we talked about feed forward, that everything is connected, fully connected, feed forward when everything is connected to each other. If we have many layers, we call it deep feed forward. If we have recurrent connection, we call it recurrent neural network. Then we have LSTM, which has a more complicated structure. Then we have convolutional neural network, which every neuron is not connected to all the neurons. They connected to only a part of a subset of the neurons in the previous layer, and etc. So based on that, we have different combinations. I believe that in 2 weeks, Sina and Eugene will talk about different architecture and how you can train them. So I'm not going into the details. But here it's only simple example. This is a ResNet with 34 layers that is invented in 2015. So they put it 34 different convolutional layers together to be able to train a model for image classification. Here they added residual connections. So between some of these layers, they added the skip connections, or VGG in 2014, if I'm not mistaken. They invented a model with 19 layers, and in the same year, 2015, they also trained a model with 152 layers, and that 152 layers, they were saying, okay, it was working better than human. So at the time, we had something that was working pretty well for image classification. For other tasks, for example, in dealing with text, right now we have transformer architecture or attention architecture, which is very complicated neural network. I'm not going into details, but for some of these models, we have some of them they have one encoder part and one decoder part. The encoder part, sometimes they have 10, 20, 40 of these blocks stacked to each other, which each blocks, as you can see, they have multiple components, and each of these components is a complicated neural network. So it's a it's again exactly like block of Lego that you put on top of each other to create a very big neural network. And the thing is, the most AI thing, the most famous AI thing that these days we are using, ChatGPT, is using this architecture. And it's estimated that it has around 1.7 trillion parameters, learnable parameters in ChatGPT. So the idea is simple, but there are many, many neurons inside those inside those modules. And before going into more details, there are a few concepts that I need to talk about. So I will talk about the different topics, then I will merge them all together to have better understanding of neural network. The first one is cross entropy loss, is the loss that we are going to train classifications. So what does it mean? Uh, for linear regression, is that okay? It's only a single line. It can separate only two classes. There are multiple ways of one versus one or one versus rest for training on multi-classes, but there is one another approach that here we use it in neural network, and that's it. That is using one neuron for each expected output. So here I have three classes. Instead of creating the line, that I have the issue with the area in the middle to find it. So I use the highest value. So for each of these neurons, which is they are corresponding to one class, I choose the highest value. So if it's closer to the line or further from these lines, this is what I'm considering by choosing the highest value. So in this case, for example, y1 is 15, y3 is 12. So y1 is the largest one. I choose this label. That's easy, but we are looking for a way to convert these outputs to kind of some probabilities. As you can see here, the distance between y1 and y2 is a lot, but y1 and y3 are close to each other. What does it mean? What does this closeness mean? So we are hoping to find a way to convert these values to some kind of probabilities. So we can say, okay, how much they are close to each other, or we can have a better understanding of the chance of each of these classes. The probability distribution will need two criteria. One of them is each value should be between 0 and 1, and then sum of all the values together should be 1. So if we go by getting the average by dividing each value by the sum of all of these values, then the sum of the predictions would be 1, but each of these values are not between 0 and 1. As you can see here, we have negative values. So this is not going to work. The suggestion here was to use the softmax. So the similar idea, but we use e to the power of that value. So again, that value divided by sum of all of them, but instead of the value itself, we use the e to the power of that value. So if we use this softmax function, then we have the values that each of them is between 0 and 1, and some of them are 1. Now I can say, okay, we have some probability distribution. If we look at the values that we have, now 15 means around 95%, 12 means around 5%, and -5 means 0%. Now we have percentage and we have a better understanding of the values. Here we need to define a loss function, but let's look closer to these predictions. So I have three possible predictions. My expectation is class 3. So my expectation is the value for y1 should be 0, the value for y2 should be 0, the value for y3 should be 1. Okay, so this prediction is definitely bad because the highest value is class 1, which is not the one that I expected. But for prediction 2 and prediction 3, the highest value is class 3 for both of them. So the prediction is correct. But this one, it says with 40%, this one says with 90%. So I need to find a way to give more weight or more value to this type of prediction compared to the one that has closer value to each other. And for that, we are using cross-entropy loss. There is a simple formula for that. I'm not going to into mathematical details, but the thing is, if I use this kind of loss function, then for a bad prediction, it gives very high loss. For an okay prediction, it gives me a better loss, lower loss, but not very close to zero loss. And for a good prediction, it gives me loss pretty close to zero. So the idea, the hope of training a neural network is to minimize the loss function. In this case, for classification, for multi-class classification, we talked about cross-entropy loss. We talked about softmax, and in many of these classification, we use cross-entropy loss. But this is not the only loss. We have thousands of different losses based on the problem that we are going to train to work with, based on some characteristic of the data, based on the architecture of the neural network that we are going to work, based on the number of classes, and etc. Okay, so based on your own task and your own problem, you need to find the right loss function. But for many classification tasks, for multi-class classification tasks, usually cross-entropy loss is working well. Okay, the next topic that I would like to, is there any question about the losses? The next topic that I would like to discuss is the regularization. I divided regularization into two different sections. Here we are seeing the first part. This is these two shapes are coming from the previous sets of slides when we were talking about the degree of polynomial in linear regression model. So here I printed the weights, those W's in our formula. If I use the degree of 3, and as you can see, this is the weight, this is a good prediction, almost. The weights are 0, 1, 0.8, 0.08. So these values are small values and close to 0. But when I train a model with degree of 12, these values of 177 minus 382, 400, these values are much larger and far from 0. So the first thing that, one of the things that comes to our mind is probably values that are closer to 0 are better. So we are not sure about that yet. But let's consider this example. This is my output. and I have two sets of W. The first one is 1, 0, 0, 0, and the other one is 0.25 for all of them. And the multiplication of these two, the result would be the same. So in previous example, we saw that lower weights is better. And in this example, we are seeing that for the same result, we can have different sets of values. So if we put these together, we can say, okay, we also want, in training a model, we want to minimize the loss. The loss was the difference between the expected output and the predicted output. But other than that, we also want to have lower weights. So for that, we can define two types of penalty. Usually we go with L2. We also try to minimize this penalty here. So please keep that in mind. We want to have lower weights or lower values in the weights. So we define a penalty for that. We define the loss function. Now we go through the optimization, the next topic that we would like to discuss. Optimization is to minimize the combination of these two losses, the loss on the data and the penalty part that we discussed for the weight. So finding this minimum is our goal in optimization. How it's worked? So we have a bunch of data. The input features goes to the model. The output goes to the data loss. Then we have the expected output. It goes to the data loss. We calculated the data loss. It goes to the total loss. Then the weights itself is the one that our model is using. Also, we pass these weights to the regularizer to calculate the penalty and some loss. Then we pass it to the total loss. This is something that we want to minimize. And by optimization is to find W in a way that minimize this loss for me or minimize this formula for me. So the hope is finding the parameter, the W, the weights in our model that minimizes this formula for me. That's the goal of optimizing. Okay, assume that the function that we want to optimize is a very simple function, x minus 2 to the power of 2 plus 1. From calculus, we know that we take the first derivative, we put it as a 0, then for that point, we calculate the second derivative. If it's positive, then that point is a minimum for us. So pretty easy. We can do it. But can we do the same thing for a very complex neural network? For one layer, maybe. For two layers, okay, it's pretty hard, but again, maybe. But what about for 3 layers? What about for 10 layers? What about for thousands of layers? What about for 2 trillion parameters for ChatGPT? Can we take the first derivative and then the second derivative and then do the calculation? That's not possible. So there is another approach, the second approach. It's not exact in all cases. It's some approximation, but it works pretty well in many scenarios. So the same function, we start with a random point. At that random point, we calculate the gradient. And then we take a scaled step in the opposite direction of that gradient. So the gradient is this way, we go the opposite direction, and we go scale the step. I will talk about this scale in 2 slides. And if I do this scale step, I will come to this point. And then I will do the same thing. I take the gradient, this interaction. I will go into this, the second point. I will continue until I reach to the point that I want. So I continue these steps in a for loop. in a loop until the maximum number of iterations is reached, or I'm seeing that okay, I'm going closer, 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 but it's not moving a lot, so I'm stopping. So there we can define stopping criteria for this loop, but the general idea is when we reach the a close point to the minimum. It's not again accurate, it's approximation, but it works very pretty well in most of the scenario. We call this approach gradient descent. Okay. In order to better understand how does it work, consider that you are in an uphill. Please don't laugh, Eugene. Uh, we are in an uphill and it's dark. There is no way to see it, find the downhill. There is no way to find the right path. We want to go to downhill. We don't know what to do. We have a small torch. We can just see around ourselves in with a circle of 1 meter, for example. So what we do, we try to find only the next step. We try to look at the surrounding and see, okay, when there is a step, when we can go, we take one small step. Then in that point, we find the next step and we continue until we reach the point that we are want to go. So that's the idea of gradient descent of the algorithm. Now let's talk about that scale that we said earlier. That scale, we call it learning rate. If the scale, the step that I'm taking is too small, it takes many, many, many iterations until reaching that point. If it's too high, so here the direction is this way, the gradient is this way, the direction is this way. So if I take very big a step, instead of going toward the minimum, I'm going further from here. Then when I'm reaching this point, the gradient is this way. I'm going the gradient is this way. I'm taking the opposite direction, so I'm going much further. I'm not going toward the minimum. I'm going far. I'm making myself far from that point. So finding the optimal learning rate is another challenging thing. It's another hyperparameter that we need to choose. The optimal learning rate or the optimal scale to taking the steps is the one that, okay, I can reach the minimum points in minimum number of iterations and not going far from the minimum point. The next topic that we need is the term backpropagation. So we said, okay, we need to calculate the gradient. We use the backpropagation algorithm to calculate the gradient in neural network. So to find the gradient, it's a complex function. It's not easy, almost impossible to calculate the gradient, but there are some solutions. And the idea is backpropagation. We consider it as a computational graph, and we calculate the gradient for all of the weights. Here I have very simple function, x plus y times z, and I have some values. And then I would like to calculate the gradient of f with respect to all of these inputs. This is my function, the gradient of f with respect to x, y, and z. The forward pass is passing all these values to our model and calculate it. So -2 and 5, here we have addition, then we have 3, -4, multiplication, we have -12. We call it forward pass. Okay, to calculate the gradient, we need a bunch of this. So here we define Q, intermediate variable, to make your calculation easier. Q is x plus y, that's inside this parenthesis, and the gradient of Q with respect to x and the gradient of Q with respect to y is pretty straightforward to calculate. And f is Q times z, again the gradient of f with respect to Q and F with respect to Z is almost easy to calculate. Bunch of these we have it already, but for example, the gradient of F with respect to X, we don't have it. So we need to calculate. Here we use backpropagation. I'm not going into the details, so I'm using my previous slides. There is no need for you to learn this, how does it work, but I'm trying to give you a general idea. So I skipped many slides here, and I'm just going to last part of these slides. So for those that are easy, we do it easily. For those that are more complex, for example, the gradient of f with respect to x, we use the chain rule formula. Based on the chain rule, the gradient of f with respect to x is gradient of f with respect to q and times gradient of q with respect to x. So for each step, it was easy to calculate. So for the whole network, it's just using chain rule. So if with this chain rule, even if I have very complex and very deep neural network, I can calculate the gradient for each step and then multiply it with the gradient for the next step using chain rule. Sorry, and continue to calculate the gradient for all of my parameters. So that's the backpropagation. Um, this is the way that we calculate the gradient. So if we define the forward path, which we calculate the output, then we have backward path, which is backpropagation to calculate the gradient in our neural network. So that was backpropagation. If I didn't go into the details, and I'm saying it's not necessary to understand all of these details to be able to use neural networks. The next topic that we are going to see is the stochastic gradient descent. The term stochastic is added to this algorithm. Here, I define a training loop for training neural network. Okay, so let's read it line by line and see what happens. So at the first line, so here I have a condition to see when my network, my training is done. It could be the performance, it could be number of iteration, whatever. Okay, until I reach that condition, I will take a mini batch, a small subset, very small subset of my dataset. Let's say, for example, I have a dataset with thousands of samples. I get a mini batch of 4, 5, 6 samples, for example. Then for that mini batch, I calculate I get the input and the output. This network is my neural network. Using the forward pass, I pass my input to the network, and I get a prediction. I call it y hat. Then I compare the prediction y hat with expected output y using the loss function. So I calculate the loss. Then if I have a regularization, I pass the weights of my network to the regularization to get the weight loss. Then I add these two loss together. I have a term lambda here to not use to use a portion of this loss to adjust a contribution of these two losses to the total loss. And then with the backpropagation or backward pass, I calculate the gradient for all of the weights in my network. Okay. Before going to the next line, here I would like to about the stochastic part. In each iteration, I use a mini batch, a subset of my training samples. Why? Probably if I have 10,000 samples, I don't have enough memory in my computer to do all of these calculations for those thousands of samples. So that's why I use a subset, a mini batch of that. So this mini batch is that again, it's another the size of this mini batch is another hyperparameter that we should use. But usually the rule of thumb we go with a value that fits into our the RAM of our computer, or if we are using GPU, to the RAM of our GPU. Sometimes we can only fit one or two or three samples. Sometimes we can fit, for example, 30 to 100 or thousands of samples. It depends on the uh, many factors like the size of the model, the size of the data, the type of data, and the size of the RAM that we have access with our computer. But this getting a subset, a mini batch, we call it a stochastic because randomly we choose that uh, batch and we go toward the direction. And this, the second part, the last line is where we update the weights. Okay, this learning rate is the scaled step that we talked about, and the gradient of all the weights we calculated using backpropagation. This updating the weights, we call it optimization. And the simplest way is to adjusting it by a portion of this gradient. That's the simplest thing to do. It's easy. So the general optimizer is an algorithm that takes us from a random point in the surface loss and take us to the minimum point in our surface, the minimum loss. So we want an algorithm for that. Definitely, ideal solution would be a straight line from the start point to our goal. It's the shortest path, it's the fastest path, but it's not the easiest. It's not always possible. For example, when we are going with the a stochastic gradient descent, it's because we are only look at some samples, not all samples. The direction is almost toward the goal, but not exactly toward that direction. So it takes us to one point. Then from that point, we get another batch. We calculate the gradient. It takes us to another point. From there, we take another batch and we continue, and we hopefully we reach the goal or the minimum loss that we want. So this is the formula for a stochastic gradient descent, and this is how it works. But we said ideally we are looking for a direct line from our starting point to the goal. There are many other algorithms. Again, I'm not going into the details. For example, a stochastic gradient descent with momentum, they added another term into the formula, which makes it a bit faster to reach that point. For example, here, if it takes 1,000 steps, probably here it takes 500 steps or lower to reach that point. Okay, so there are some modification of that. There are many different optimizers that we can use. The simplest one is the stochastic gradient descent, or SGD, which we saw the formula and the idea behind it. SGD with momentum, it adds another term to that. They call it velocity, and it causes to reach the point, the minimum point a bit faster. Then we have many other many other optimizers that, as you can see, they are developed on top of each other. This one added the terms of velocity. This one consider two types of velocity. This kind consider more different variables, and etc. But which one we should use? Usually, my suggestion is to go either with SGD with momentum, the momentum approach, or AdamW. These two are in practice. I'm not saying again the choice of optimizer is another hyperparameter, and you should choose based on your validation set and see which one is work better for your specific need. But there are tons of these hyperparameter, and if we want to try all of them, and sometimes training neural network, it takes hours, days, sometimes months to train a neural network. So you cannot compare, okay, all the possible learning rate, all the possible value for lambda, all the possible architecture, all the possible optimizers, and all of these. So that's why I'm giving you these suggestions to reduce the search space on your parameters. And usually, in many of the examples, these two are working better than the other. SGD with momentum and AdamW. There are papers that they show that these two are working better. In some cases, AdamW is better and faster. In some cases, momentum is working better and faster. But both of them are good enough. Okay, so choosing the optimizer was one step, and now continue with the second part of regularization. Okay, we saw this figure on the right. We said that if the model is too simple, we have underfitting problem. Underfitting problem is where the model is not working well on test and train set. If the model is too complex, we have overfitting issue, where the performance or the is high on training, or the error on training is very low, but the error on test is very high. We call this situation overfitting, and it happens when the complexity is very high. So the optimal solution is in the middle. But sometimes, let's say that you have very complex data pattern, and you cannot go with very simple model to solve that. Okay, you have a very complex image classification. You want to prevent overfitting, but you cannot go with a simple logistic regression problem algorithm for that. What we can do? So the first approach was to reduce the complexity, use a simpler, a bit simpler model. That would help. But if it's not possible, try to add more data. That's the best thing that you can do. But most of the time, it's not possible. I should have mentioned this one at first. So first, try to add more data. If you couldn't, then reduce the complexity. If you couldn't, then add regularization. We saw the weight regularization in previous slides. Now we want to talk about dropout and early stopping. Dropout is something that there is no must in life, but I would say that you should use dropout whenever you want training neural network. It's a must for me. Okay, so don't forget to use it. The idea of what is dropout. So we said that one of the issue with overfitting is the complexity of the model. In dropout, we want to reduce the complexity. How? Make the model simpler. How? In each iteration, for each batch, we shut off bunch of the neurons in our neural network. Okay? So, for example, I'm passing a sample to this neural network, and instead of using all of neurons, I'm using a subset of these neurons. Okay? and I train the model only on these neurons. Then for another batch, I again do the same thing, but this time I shut down bunch of other neurons. So at each batch, I use much smaller model, but the model that I'm using is different from the model that I'm using in another batch. And I continue that during the whole training. The question is, yes, is what should be the percentage of the dropout for neural network? Um, Again, it varies, as you mentioned, it varies based on the application or architecture. Uh, let's say that I'm dropping out 50% of the neurons, okay? And I have, let's say that I'm dropping out 80% of the neuron, okay? If I have two layers, it might not work. If I have four layers, it might work. Then if I have thousands of layers, then 80%, again, it might be losing the many parts, because when you're removing one neuron from one layer, you are also removing the connection from previous layer and the next layer. So you are removing many other information from the network. So it's not good when you cannot use very high value when the network is very large or very low. Uh, from literature and from experiment, there are two values that I've seen people frequently use. That's a 50% and 20%. That's my suggestion. If you want to try it, I would say, again, it's a hyperparameter. You have to try to see which one is better for and works better for you. But usually I've seen that people try these two, 50% and 20%. So if the model is not uh, too too big, and you have you don't have enough training data, and the chance of overfitting is very high, I would suggest 50%. If you have enough training samples, you just want to improve the performance of your model, then I would say 20% would be a good choice for dropout. Okay. So the idea of dropout here is, I'm expecting that this subset can learn the same thing that I want with the number of samples, and then another subset can learn the same thing. It's kind of merging bunch of ensembles together, but they are it's not ensemble at all, but the idea is we can look at that as kind of ensemble, that we have many small networks, neural networks, that they are working together to do the prediction. There are one consideration when so if you are using any library of it, and in the library you are specifying the dropout, that's fine. But if you are doing some experiment on your own, you should consider this point, that this value, the output here in each neuron, actually, not only the output, is coming the input only from three neurons, for example, here. Or this one is getting the input only from two neurons here. During prediction, this dropout is only applying during training part, not the prediction part. For prediction part, we are using all the neurons and all the connections. So this specific neuron, for example, here is getting information only from two neurons. But the same neuron, now it's getting information from five different neurons. And if you remember, we are adding all of these information. So the value that I'm getting here is a bit higher than what I was getting during training. So there is a scaling that you need to do here if you want to implement or work with Java by yourself. But if you are using any library like PyTorch, TensorFlow, etc., it's already considered in part of the implementation. So there is no need for you to uh, be worried about that. Matty, did I answer your question? Or okay. Uh, Now we talked about choosing the hyperparameter and validation and all of these things. Let's see how we use it in training uh, of neural networks. So we didn't go to the training of SVM and logistic regression. Uh, for SVM is pretty complicated, even more complicated than neural network. For linear regression is very similar, but because all of these are done under the hood of scikit-learn, uh, and we are not seeing them. We just call a function dot fit and that's it. But for neural network, we can use scikit-learn as well, but scikit-learn is not very flexible for working with different neural networks. So usually if we want to train a neural network, especially with more layers, more complexity, and make it a bit deeper, we need more flexibility, and we probably we need a better uh, hardware such as GPU compared to CPU. So scikit-learn is not supporting that. For this reason, we are using PyTorch or TensorFlow or similar libraries. For these libraries, the implementation of training is something that we are working with, and there are many hyperparameters that we're working with them. So that's why we are going a bit more into the details of training neural network. Okay, so this part here to calculate the loss and the update the weights is the same couple of lines that we signed in one of the slides earlier. So I combine everything into those lines into two lines. So for each batch in train set, calculate the loss, and based on the loss, update the weights. When we see all the samples, let's say that I have 1,000 samples in train set, I use batch size of, let's say, 50. Then after 20 iterations, I'm seeing all the samples in my training set. So these iterations that I'm seeing all the samples, I call it one epoch. Okay. So again, this is not a rule, and the implementation on different libraries is completely different. But here I want to give you a general idea. Uh, for example, I want to train my model for 10 epochs. That means I want my model to see the samples 10 times. Okay. So I define a for loop from 1 to 10. For each of these epochs, I train the model on the whole training set. After I'm done, then I calculate the loss on validation set. I calculate the accuracy on training set and the accuracy on validation set, or any type of metric that you are using. So what happened? In bunch of iterations, I do the training. So here I'm using the terminology of one epoch, and one epoch I said is equal to seeing all the samples. But there are other implementation that they use other definition. For example, they say, okay, every 1,000 batches. There is no definition of epoch. But the general idea is you train for a bunch of iterations, then you calculate the performance on validation sets. Then you continue training for a bunch of iterations, then you calculate the performance on validation set and training set, both of them at the same time. Okay. So we need this to do this calculation of validation to be able to do some get some conclusion about how good we are training. Okay, these figures only we are not looking at validation loss. We are only looking at training losses. And if we draw the figure of the training cells over different number of epochs, it gives us some understanding of how well we are training it. Okay. If we look at this red line here, this is the general shape of a good learning rate and a good training procedure. This is something that in general we are trying to find. So here on the left, we have a similar approach. It comes down at with higher speed, then they reduce the speed, but it continuing to going down with lower speed. And sometimes we stop training when we be satisfied with the result. Okay. One thing that we can conclude from this figure is there are many different things, but one of the things is how good is our learning rate. For example, if I use very, very high learning rate, my loss would increase during my training. So it would be discarded training. There's no training in that, and so if you see, okay, your loss is going up instead of going down, you know that okay, you are choosing a very high learning rate. You reduce the learning rate, so it continues to going down, but after a few steps, it's stopped going down, and it would be a vertical line and continue going there. Again, it's an indicator that your learning rate is higher than expected. If your learning rate is too small, it's very low, you have this improvement in your loss. It's going down, but the speed is very low, and it takes many iterations to get the performance. It's always going down, but it's very slow. So a good learning rate is going fast at first, then reduce the speed, but it continues to going down again and again. Just a practical note here. Sometimes, this is not in this slide, so I'm just mentioning it. Sometimes we start with a high learning rate, we continue for learning, and we see, okay, there is no improvement after a few epochs. One thing that you can do, and is very good in practice, is then you reduce the learning rate when you see no improvement. So you start with a high learning rate to have a very fast improvement. Then when there is no improvement, reduce the learning rate. You see some improvement, the improvement stops, reduce the learning rate, and continue that until your learning rate is very small, or if there is no improvement, even when you are reducing the learning rate. It's just a very practical approach that we use in training most of neural networks. So consider that it's not mandatory to keep the same learning rate during the whole training. You can adjust it during the training. Okay, the previous figure was only considering the data loss, but we can compare the loss of training and validation, or the performance of training and validation. In general, we want to have a model that is working good on both training and validation. And we would like that to have the performance of them similar to each other. So if there is a big difference between the performance of validation and training set, that means there is something wrong and you need to tweak your model, change the model, or change some hyperparameter. But there is one more thing in terms of regularization and preventing overfitting. You choose a good model. It's a bit complex, a bit more complicated than what your problem and your data is. So what you can do, if you continue training, the performance on training is going down continuously. But the performance on your validation set going down for a couple of epochs, but after that it's going higher and higher. Okay. So the idea is to find this point where the performance of validation is at lowest possible and then stop training. We call this early stopping. This is another solution to prevent overfitting. One of the reasons that overfitting can happen is also training for too long. And overfitting is memorizing the training samples. If the model memorizes the training samples, it gets very good performance, sometimes 100% accuracy on training set. But when it memorizes, it's not learning the pattern. That's why the performance of validation would be much higher. Okay, that was the last slide for today. If you have any question, I would be happy to try to address them.
Thank you, Farhood. Very, very comprehensive basic concepts introduction. If anybody has any questions, please go ahead. I guess I can start off with a question. Wait, before you started introducing all of the T4 network building blocks, you showed some of these more complex architectures, such as VGG transformers and for example, someone new to the field, do you have any advice on how to get more used to it into understanding these architectures figures and translating that into actually coding them and sort of just understanding what's going on in the paper or figure? If you were to go back to the VGG part that you architecture that you have.
Um, for someone that wants to start, I would suggest to go with very simple neural network. Start very simple to understand how neural network works. For example, how the loss is going down with different learning rates. That would be really helpful before jumping into much more complex neural network. Because the idea of all of them are similar. Okay, it's really just like playing Legos. So adjusting learning rate has the same effect on a 2 layers neural network or 10 layers neural network or 100 layers. The effect of learning rate is the same. But if you're training with very big neural network, it takes much more time to train it. It requires much more data to train it, and because of all of the variabilities that you have in your training, it's make it hard to understand what is happening really. So my suggestion is start very simple with very simple neural network and with very few toy example to have an understanding of how each of these components play effect. For example, if you change the learning rate, if you change the dropout, if you change the number of layer, if you change the number, keep everything the same and only change one of these to see the effect. And then when you have better understanding, uh, when you have an understanding of how each of these hyperparameter works, then you can much easier, you use them much easier on my complex neural network. Then you see, okay, my learning curve, my loss is like this shape. I saw it when I had that example. So and that in that example, I reduce the learning rate. So probably I do the same thing, I get the same result. So it's not like walking in the dark, because really hyperparameter tuning is walking in the dark. You randomly select different hyperparameter to see which one is working better. But if you have some intuition about effect of them, then you can have a better guess on choosing them and lower your search space.
Thank you. Matsu has a question in the chat.
Yeah.
You sometimes see very fancy learning rates decay, such as cosine annealing. I've never heard of that one. I guess the best is to try a bunch of them and see what provides the best result. That's this question. Do you agree?
Um, Generally, yes. Yeah, you have to try, but uh, there is, for example, yes, there are many fancy uh, learning rate decay approaches. So for those who doesn't know, learning rate decay is meaning we reduce the learning rate after a few epochs, um, and it instead of going with a fixed learning rate. And there are some algorithms to do that. One of them is the one that they said we reduce it when there is no improvement. Um, but there are other algorithms that they automatically, for example, divide the learning rate by the value or reduce the value from that after a few iterations. And those, how many iterations or how much it reduced to decay is calculated based on some algorithms. Um, the first answer, yes, you have to try different. But then there is a personal opinion. So many people they prefer to use these algorithms, but I'm not a fan of those. Um, and I'm not saying they are bad, they are working much better than my suggestion. But the thing is, using them in the right way requires to find the right hyperparameter for them. For example, if you want to know uh, to for them to work very good, you need to know how many epochs you need to train a model. And how many epochs is a question for me, for myself. Is 10 epochs enough? Or I need 100 epochs? Or I need 1,000 epochs? So this is another hyperparameter that I don't have the answer. And in order to use, for example, the cosine annealing, but I want to use that, I need to know the number of iterations I want to train beforehand. And this is the information that I don't have it. So that's why when I'm starting a new problem, when I don't have any idea about the problem, the number of epochs and other hyperparameters, I go with reducing the learning rate whenever there is no improvement. But if I have more information, then I will use other better algorithm, or in PyTorch we call it a scheduler, other scheduler to adjust the learning rate for me. Now that we talked a lot about the uh, adjusting learning rate, let's talk about another adjustment in learning rate. So we said that, okay, we start with a high learning rate and we reduce it either based on some algorithm or based on some criteria. Uh, there is one more thing that is used. So this is very useful for most of neural network, if it's small or very deep. But then there is another trick that is useful specifically when we are dealing with very deep neural network, and very deep, I'm talking about billions of parameters, like Llama or GPT like language models or vision transformer, these types of models. And that is one of the steps. We said that we start with very random weights and then we adjust the weights until we reach the uh, minimum loss. At very beginning, the randomness is a lot. And because of that, the gradient is random. So it takes time for the optimizer algorithm to understand really what's going on, where is in this surface and which direction it should go. And because it's random, there is a chance that we take some steps that instead of making us closer to the minimum, makes us going far from the minimum. That's why for very few steps, let's say 100, 400 iteration, not epochs. So one epoch, maybe it's 10,000 iterations. For 100 iterations, for 400 iterations, I start with very low learning rate, close to zero, and I increase the learning rate. Let's say that I want to use learning rate of 1 to the power of minus 5. I start with zero, and with 400, I increase it until I reach the learning rate that I want. And then from that point, I started decreasing. So I don't know if I can have something. Yes. So if it's my iteration and if it's my learning rate, and this is the learning rate that I define in my hyperparameter. So I start with zero for few steps until I reach, and then I will use any of those algorithms to decrease the learning rate through training. So this part we call it warm-up. This is also useful if you are training with very deep neural network.
Thank you, Farhood.
Thank you. I think if there is no more question, you're welcome.
Yeah. Thank you, Matthew, for the question. Yeah, I think we can wrap today up. Thank you so much, Farhood, again, for the wonderful introduction for classical AML and before neural network. And we'll see you guys back tomorrow for 11:30 at the it's going to be Farhood again on a practical session for what we talked about today for about an hour and a half in Python. Yeah, have a great rest of the day. Thank you.
Thank you, everyone. Bye-bye.